Dear YouTube, what the hell? Oh, it works. All right. Let's see if the stream link is different. I'm pretty sure it is. Yeah, it is. All right, let's see if we can do a switch over. Come on. Can somebody in the new stream chat type something and say that you guys can hear me all right and all of that stuff? Can somebody in chat type something that says that you guys can hear me? Because otherwise I have no idea. The stream's bitrate is lower. Why do I care? All right, cool. So let me close. Actually, wait. All right. Let's assume that people will move here. All right. So let's start. I have no idea how this will go. This was not planned or anything like that, but my plan for this stream is I have no plan. So the way it's gonna go is you guys are free to ask questions in chat about topics you'd like me to talk about, and I will reject the topics that I don't like, and I will talk about the topics that I do like, and then hopefully it's gonna be interesting and productive for everybody else. Great. Do I have to start like banning people for all right. This was a bad idea, wasn't it? Actually, let's just do this. Oh, all right. Actually, can I switch to the... No, it's probably fine. I'm gonna try to moderate the chat. How the hell didn't I... This tells me that YouTube needs better filtering capabilities. Alright, nobody knows what the stream is about. Somebody has a ray tracing question. So yeah, let me just talk a bit about, oh my god. Please only ask technology questions, and also, alright. I kind of didn't really know what audience I'm getting because I'm being followed by a bunch of people on Twitter, and who knows who they are. So let me talk a bit about things that, so let's see, like in terms of legitimate questions on the stream, somebody is asking about ray tracing, and I can talk a bit about my general views on ray tracing. Somebody is asking, could we ever get lava? And that's a Roblox question, which is kind of less interesting to talk about. So let's start. I'm going to talk a bit about ray tracing, and please feel free to ask questions about other topics in chat, and then I'll kind of pick and choose. So ray tracing is interesting. I actually have a ray tracing compatible GPU. Like I bought an RTX card a year ago or 2 years ago. I didn't really have time in the beginning to experiment with this, and right now I don't really have a strong motivation to experiment with this for some reason. So, but here's my thoughts on this. I think you can think of ray tracing in two ways. One is, let's look at the renderers that people use, like production renderers. Hold on, I'm gonna have to moderate the chat, so it's gonna take a bit of my attention, unfortunately, which is not great. Can people please stop doing this? I realize it's like weird to ask trolls to stop trolling, but you guys are kind of getting in the way. The stream is not to troll the stream. So you can think of ray tracing in two ways. One is, here's the new way to render things. Everything should be ray traced. Maybe you want path tracing for everything. Maybe this tells me that YouTube moderation is not great. Maybe you don't want everything to be path traced, but maybe you want a render where there is a really, really strong ray tracing component for some part of it, right? And I think this is all cool. The issue that I see in the first release of ray tracing, and I think this is getting steadily kind of fixed, is that when NVIDIA first released their ray tracing library, it was effectively a black box. You didn't really get access to the specific bits of hardware that make ray tracing fast, which seems like it's fine, which it is. But okay, thank you. Hold on, I need to. I'm gonna delegate my moderator responsibilities to Redbearded Joe. Thank you, Redbearded Joe. Let's hope the chat gets better and I don't have to worry about this. So, there is an RTX hardware, right? And NVIDIA doesn't talk too much about what exactly the RTX hardware does to accelerate ray tracing, but there are some bits of hardware and software that make it fast. The problem is the interface to these bits of hardware obscures them a bit. So for example, it was impossible up until very recently. There's a new extension to some of this stuff. It was impossible to say I have a fragment shader and I want to cast a few rays from the fragment shader to implement shadows. What you had to do is you had to have a deferred setup where you have a fragment shader, it outputs depth, or like there's just no fragment shader, you just have a depth pass. Then you have a ray tracing step that takes the depth, creates the position, and casts some rays, puts the results somewhere else, etc., etc. Which for some render setups is not a problem. I think it's like a pragmatic solution, but it kind of limits the use cases for ray tracing, right? And also the ray tracing, when it shipped, it was effectively two complex parts. One is the ray tracing, as in I want to trace a ray through geometry. I want to get the result, right, which is like a point or like an object, etc. And then I'm going to do something with this. And then the other really complex part is the objects in ray traced scenes have materials, or actually they have shaders that execute when the ray hits. And so the way this works is there is this complex GPU side scheduling or mechanism that dynamically says, well, the ray hit this object has this shader, I need to run this shader, but actually I don't want to run this shader on just this one hit. I want to aggregate hits and then schedule some GPU workload. And again, all of this is not exposed to the general public, right? There's like some internal driver magic that does this. Redbearded Joe, feel free to ban everyone. Well, not everyone, but like I trust you to figure this out. So the nice thing about ray tracing is that if other vendors catch up, which I mean right now they're only available, commercially available, I guess, GPU, right? That supports ray tracing as an NVIDIA GPU. There's like talks about, I think both Microsoft and Sony said that their consoles are AMD powered and will support ray tracing, so we'll see how that goes. But the short story is once all vendors adopt ray tracing, my hope is that ray tracing gets decomposed into specific primitives. One is I have a scene and I want to trace rays through that scene. There's a BVH for this, etc., etc. And then the other one is the GPU scheduling, where you say, hey, I want to just schedule some work from a shader onto a GPU course, right? And when we get these two individual bits, the amount of my interest in ray tracing technology will increase, because it's not just ray tracing at this point. It's like there's these two general primitives. But today, I mean, I think one issue is, my understanding is a lot of games that have shipped ray tracing support, there's not that much of an impact in terms of graphics quality. Like there are extreme examples where there is ray traced Minecraft, right? And that looks cool. But even if you look at the Quake 2 demo that NVIDIA released, right? It looks much nicer than Quake 2 did, obviously, but with traditional modern rasterization technologies, you could get the same picture with less power draw, etc. So I think it's early to say. Yeah, this will be uploaded to YouTube after the stream has finished. So it's early for ray tracing. When it shipped, it was in a very, very different spot, right? There's steady progress right now, both in terms of APIs and in terms of drivers and in terms of hardware. So I feel like really in a few years, we'll be able to tell kind of what the real consequences of this are, right? I'm like less excited about ray tracing per se, because I am honestly used to the job of a graphics engineer is, given the hardware that has certain capabilities, certain restrictions, figure out what's the most efficient way to use that and to achieve the target picture quality. So to me, it doesn't truly matter that the render is just fully path traced, etc., because I don't feel it's super viable in terms of power consumption. But to me, it is really viable to expand the set of tools that a graphics programmer can use to achieve the result that they need to achieve. So that's the general thoughts. Here you go. So let's see. What do I think of mesh shaders? Do I think is the future? So mesh shaders are actually very interesting. Kind of, it's like a good segue in a sense to talk about mesh shaders. I am really excited about mesh shaders. There's two reasons why I'm really excited about mesh shaders, and one is I think it's just a very neat construct. There's a very, very clean API, right, for this. It's starting to be adopted. It came out as an NVIDIA extension. There is now a DirectX preview of mesh shaders. There is like a recent article on this from November 8, right? So this is like really, really fresh on the DirectX side. The terminology here is slightly different. The task shaders from NVIDIA are called amplification shaders here. But, so I'm really excited about this for two reasons. One is I like the design. I think it's clean, it's pretty easy to understand, it's pretty powerful. If you are curious about kind of the practical use of mesh shaders, I actually did a series of streams, if you don't know about that. You can look at this on my channel later. It's called Niagara. It's a rendering project that I did where I wrote a Vulkan renderer from scratch, where I used mesh shading and some other interesting techniques. So it's a really, really clean extension to the set of shaders that we have, which is great. The other bit I'm excited about is actually highlighted here, which is reinventing the geometry pipeline. So mesh shaders have a long-term possibility. Long-term. Like we are talking, 10 years or something like this. To replace the existing stages. The problem with rasterization pipeline is that it is getting really complex. So the real issue is, right, so like there used to be in Direct 3D 7 days or something like this. There was like hardware TNL, and then there was very, very, very simple. There's not really a shading setup. It's like just there's a texture that you sample and you're done. And then there's like some blend stages that, technically, basically there's like raster, and then there's some blend bits about drop. So then in Direct 3D, I think 8 era, the raster stage, after the raster stage, the thing that samples textures, etc., it became more configurable. So then it was kind of like there's hardware TNL. I'm really bad at drawing ampersands. Anyway, so like there's transform and lighting, which is mostly fixed, right? Then there's raster, which is mostly fixed. And then there's texture combiners, which you could say, I want to sample this texture from this texture coordinate, and then I want to sample this texture with this texture coordinate, and like blend the results together or something, and then there were several stages. And then there's still fixed function ROP, which is a blend debuffer, stuff like that. Then the transform lighting stage got replaced with vertex shaders, right? And then the texture combiner stage got replaced with pixel shaders. And in early days, this was all very primitive, right? But like with Direct 3D 9, the capabilities of both the vertex shaders and the pixel shaders were expanded reasonably substantially. So this was pretty simple, right? There's now 2 programmable stages, and if you just look at the geometry part, there's just one, there's just vertex shader. Cool, easy to reason about. Then it kind of went downhill, because with Direct 3D 10, I'm not really sure who the initiative comes from. It's maybe NVIDIA, it may be Microsoft, it may be a combination thereof. They said, well, like it's really, really necessary to generate geometry on the GPU. So let's add geometry shader stage. Cool. The problem with that was that the geometry shaders were slow and limited. So it's like if you wanted to do something simple, they were slower than not using geometry shaders. If you wanted to do something complicated, you just couldn't do this. Then with Direct 3D 11, the tessellation stuff came in, right? And tessellation adds like 2 more stages, hull shader, domain shader. Actually, it's sorry, I have to keep scrolling because I'm like drawing on my Surface Pro. So actually, it's sort of like it's complicated because the hull shader has kind of 2 parts: the part that runs per patch and the part that runs per control point. So today, right, there's like 4 to 5 different shader types depending on how you count before the rasterization. So all of this still feeds into the raster. And still, they are kind of limited, and geometry shaders are still kind of slow. There are some exceptions to this rule. Tessellation is sometimes useful, but not a lot of games actually use it productively. One common use of that is terrain tessellation, but beyond this, it's kind of a hit and miss. So geometry pipeline got really bulky and inconvenient to work with over the years. And of course, every driver has to implement this. GPU architectures don't really work this way. There's bugs and all of this stuff like that. So what I'm really hoping for is that the long-term future looks like this. We have 2, I still think we should have 2 types of pre-raster path. One is the old vertex shader stuff, which honestly, for a lot of workloads, it's enough. It's fine. This path is really, really easy to program for. It's the old mental model. Everybody gets it. It's easy to explain. I can explain it in like, a minute. The other one is the mesh shader, technically the task shader runs first. It's like task shader, mesh shader, or DirectX calls this amplification shader, so amplification shader, mesh shader. And then it goes to raster. And then we take all of the old stuff, and then there is like in Direct3D, there is some driver compiler that takes the old shaders and recompiles them on top of task shader infrastructure. And so what I think we'll get out of this is, if you want to write simple apps, they still work through the vertex shader path, it's fine. Like if a driver developer wants to do this, they can compile vertex shader to the task shader, mesh shader stuff, but it's kind of more complex to do that. And as a result, we get a pipeline that is more extensible because task shaders, mesh shaders are richer. It is simpler, it is more performant, hopefully, and there's just benefits all around. So yeah, I'm like really excited about this. There was a question about AMD. Based on publicly available information, let's put it this way, it's not clear if AMD is going to implement task shader, mesh shader stuff, but usually when a feature appears in Direct3D 12 or 11 or whatever, it usually means that either a future GPU generation, or in rare cases maybe even a current GPU generation through a driver update, gets support for this, right? The other thing is in Direct3D 12, the amplification shader stage is optional. NVIDIA supports both mesh shaders and task shaders, amplification shaders, but the Direct3D spec, the amplification shader stage is optional. I suspect that this is to make it easier for vendors to implement partial support for this feature. So yeah, I am excited about this, but this is a long-term opportunity, to be clear, right? If you're making a game today, it's kind of a distraction. I think this is more like if you're doing prototyping for the future, or if you're starting to make the engine today that will be like kind of live in several years, in like 5 years, then it feels interesting to start thinking about that. So it's a long-term play. So there's a great question about preventing the collapse of civilization by John Blow. Let me read the rest of the questions briefly, just to make sure that there are no follow-ups on mesh shading stuff. Does any vendor support the X12 mesh shaders? I don't know. I suspect that maybe NVIDIA doesn't have a driver update for this yet. I honestly experimented with mesh shaders only through Vulkan. I have been just watching the mesh shader stuff as it exists in Direct3D 12 through like reading blog posts and things like that. So I don't know, right? Whatever. Would you ever consider doing a tour of my FAR setup? All right, there's a lot of really great questions. So I'll have to actually answer all of them. Okay, great. Let's just go in order. So preventing the collapse of civilization by Jonathan Blow. I have watched this talk. I really love this talk. So John has, generally speaking, as far as I can tell, I mean, I've never met him personally, based on watching his videos and, like occasionally exchange with him on Twitter, I think his opinions tend to be a bit too polarized for my taste. I mean, this is kind of what the talk is about, right? The talk is about, hey, it's all kind of going downhill. It may not be super obvious that it's going downhill, but it is. And our software stacks tend to be really, really bulky, etc. And this is like a problem. And if we continue down this track, then we are doomed, roughly speaking. I don't think the technology is doomed in that way, but I do share a lot of the discomfort that John has around the state of the technology. There's two ways to look at this, right? So if I look at the web stack, and I forget what specific examples John has in the technology land, but if I think of the web stack, right? So there's like, web is really big. There is a new tendency to ship desktop apps. that use Electron. I mean, a lot of people love VS Code. VS Code is running a web browser inside it, right? And I have two thoughts on this. One is, well, I kind of hate it all, in the sense that if you look at the complexity of this technology stack, if you look at the performance of this technology stack, ability to reason about bugs, ability to reason about performance, it's like really bad, right? Uh, Quick example, I personally tried to use VS Code. I think it's a fantastic editor. I love the editor. It's great. I cannot use it. Why? It's because for me the latency of text input is unacceptable. As in, I type text, and the delay between me typing text and the letters appearing on the screen triggers some subconscious like discomfort for me, and I feel unhappy and frustrated while typing text in VS Code. Especially, and I ranted about this on Twitter before, especially like if you're on a laptop on a battery power where your CPU doesn't run at like 4.8 gigahertz boost, right? And it runs at like 1 or 2 gigahertz, suddenly it's like 2 to 3 to 4 times worse, and it's really, really painful for me. So, to my understanding, this is because this is not because the team doesn't care about performance at all. It's because the stack that they're working with is so deep that it's really, really hard for them to make progress. The other side of this, though, is web is really accessible. It's really amazing. I've been doing some work lately on GLTF and WebGL and things like that. And like, me being able to type like something and have 3D models appear on screen, and then I can go into the debug console, and then I can look at sources, and then I can place a breakpoint and it works, and I can inspect the call stack, and I can do performance profiling, and etc, etc, etc. So, which is to say that through the massive popularity of the web stack, by necessity, I think there is a lot of technology, and some of this technology is actually better than what we have in native land. There's a lot of technology that people have built that really works. Um, Quick aside, I mean, my day job sometimes involves debugging, profiling, etc. Android applications. It's a trash fire. Like, it's really, really terrible. There's no web there. It's like all native. Compared to this, I actually tried to debug and like step through, etc. This web page that I just showed you guys like several months ago, I don't remember when it was, on an Android phone, and it just worked. It was an amazing experience where I take a phone, I open Chrome Developer Console on in like my desktop Chrome, I connect them, it works. So on one hand, I think like yeah, it's a big problem that these stacks are really complex, etc., etc., and like I think we should be solving this problem. On the other hand, I think it's less bad than John thinks, and there is only so much complexity that humans can keep in their heads, and it's a natural tendency then when this complexity goes past a certain threshold, some other solution emerges, and if the solution is technically superior, it will win. So John is building a new programming language. I like a lot of things about this programming language. The proof is in the pudding. If his language is so much better, it removes so much cognitive overhead, it will win and the problem will be fixed. If he weren't doing that, there's other things that other people are doing, right? That also try to find a different balance between complexity and kind of usefulness, right? So I think the whole system, from my standpoint, kind of naturally evolves, and I think it's a mistake to say that well, it's just in decline, and if there's no radical action, we are doomed. I suspect we will figure this out. So, would you ever consider doing a tour of your FAR setup, shortcuts, plugins, etc.? Yeah, I mean, it's kind of interesting. I use FAR Manager. It was really, really popular, maybe still is, in ex-USSR regions back in the day, like 20 years ago. Looks kind of like this. The there's nothing super special about my setup. I don't use any plugins. I don't use any shortcuts that are not built in. It's just vanilla FAR. I'm trying lately to force myself to use a bit less of FAR and a bit more of terminal. Before, like Windows terminal tends to be pretty janky, Windows command line shell is terrible, etc. But I work a lot in Windows subsystem for Linux these days, like this is that. And I tend to use FAR less often. So as you can see, I didn't even have FAR running, and I had the the Windows terminal with the Linux shell running. So I use FAR a bit less often these days. It's still a fantastic tool. I just find myself slowly gravitating towards kind of more command line and less dual panel shell, dual panel like file explorer workflow. FAR still beats Windows Explorer by like giant margins. So if I need to, if I am not satisfied with like just the like ls cd etc., then I basically go back to FAR. What's the earliest we can expect Features Brightface 2.5 to ship February? Yeah, it should ship in January. We actually tried to ship it fully this year. We shipped like half of it. We shipped most of the internal setup, but we didn't ship a few user-facing bits because we kind of ran out of time on some stuff. So yeah, I think it should ship in January fully. What do I think about ray marching for signed distance fields in games? That's a good question. I only know of one production game that does this, which is Claybook, which is a really interesting showcase of this technology. I think it's really neat in multiple contexts, but I don't know if it is versatile enough to be a viable replacement. But like I think so I guess it's a really interesting research topic, and Claybook's example clearly shows that you can ship a game on this technology, but I'm not sure that it's as widely applicable as you could otherwise think. But there is a lot of nice things about this. So for example, one of the big challenges in computer graphics is in real-time computer graphics is level of detail, and there's a lot of work, like there's a lot of solved problems, I guess I should say, in level of detail, but the geometry level of detail is still an unsolved problem, in the sense that in an ideal world you would expect that you have an object really far away and you're shading a pixel that covers this object. Well, you should get the geometry kind of coverage on that pixel that is effectively integrated coverage over that pixel of many small rays, which is impractical to do, but this is kind of what, if you think about multi-sample anti-aliasing, this is kind of what it does. It does a much more high resolution coverage mask and then kind of collapses the results back into one pixel. So it's cool and all, but it doesn't truly scale. So then what people have to do is they have to do geometrical LEDs, and there's like many problems with the geometrical LEDs. If you talk about ray marching, the interesting thing about ray marching specifically through basically sun distance fields, the interesting thing is in many cases it is practical for you to pre-build some sort of hierarchical representation far away, so that when you ray march, you don't actually ray march, you cone march, right? So you like you trace cones, and when you trace a cone, if your cone hits a node where there's a lot of detail inside this node, but there's a coarse representation of this node, then you just get the results from that node in like minimum time, which is good for performance, but it's also good for reducing aliasing, etc. So like basically, if your representation of geometry is not triangles, but it's distance fields or some compatible representation, what you get for almost free, not quite free, you have to work to get it, but it's much easier to do, is really good geometrical LED. So that I think is really cool. And also if your geometry, if your like distance function is parametric, then not parametric like implicit, right? then you can compute it at a high resolution or low resolution, even for close-up scenes, right? So it's like you can get closer to the object, you can get higher geometry fidelity. So that's all cool. In general, I really like SDFs. I don't know if it's truly practical yet to just kind of frame arch through them as a game, right? I'm not sure. Like Claybook works, it's cool. There's a lot of optimization, there are a lot of really hard optimization challenges that the Claybook devs had to face to get it done. As far as I know, I don't know how many platforms they actually did ship on, but I know they experimented with mobile, and it seems like it sort of works. But I think there's a bit of extra. Like, I think we're not fully there yet. I think there's more. I think the hardware needs to step up a bit, I think. And also, I think there is more kind of. Not just research, but there needs to be more work to take the techniques, for example, that Claybook Fox used and kind of commoditize them so that it's easy enough for me to build something like this if I'm not an expert on GPU optimization or something like this. Which my perception is right now you have to be an expert on GPU optimization for this to be practical. I haven't built a renderer like this, but definitely from looking at Claybook, it's kind of really necessary to have to dig really, really, really low into the GPU stack to get performance that is acceptable. So, but it is interesting. There's like things around SDFs that are not fully understood that are not, I guess, as well researched as other things. Like how do you do translucency is not clear, and so in normal games, I guess in AAA games in general, translucency is a dodgy subject due to deferred shading and things like that. But worlds without transparent objects are really boring. So that is where SDFs are not as optimal because some techniques to work with SDFs don't work as well. What have I been working recently besides Roblox? Anything interesting going on with Mesh Optimizer, for example? So, yeah, my only spare time project right now that I'm actively working on is Mesh Optimizer. The short story is this. I'm trying to focus a bit on specifically the GLTF applications of Mesh Optimizer for kind of two reasons. One is I think the GLTF ecosystem needs a really good compressor, etc., and I think existing offerings are not very good. The other one is GLTF stuff tends to take a lot of time to standardize. So I want to be there early so that then I can just spend like a year doing other things and then and then in background do standardization stuff, and then in a year everything just lined up. So yeah, my current focus on Mesh Optimizer is twofold. One is work a bit on the GLTF pack, which is this GLTF processing tool that takes the GLTF file and makes it more optimal. But the other one is to finish the vertex and index compression work that I did some time ago. So there's existing geometry compressors in Mesh Optimizer. I'm like 70% happy about them. And I want to be like 90% happy about them, and then I cannot think about them for a while. The other thing that I will look into is simplification. So I did some work on simplification. I'm not fully happy with this. In fact, it's kind of I want it to just work. It doesn't just work right now. I think there's like 5 issues open on Mesh Optimizer repository, and like 4 of them are about simplification. So, but like my plan is finish geometry compression stuff. I'm hoping to do this over the next few months. Then kickstart the GLTF standardization stuff. I already almost got one extension standardized in GLTF, which is awesome. It's my first extension in really any ecosystem. And then after this, I'm gonna do more simplification work, I think. On Twitter, I changed from tech director to tech fellow. What happened? It's a promotion. Tech fellow is it's a less common role, I guess, than tech director, so not everybody knows what this means, but it's kind of a just next level. You can Google tech fellow. It's a position that some other companies have, like Intel and some others. How long have I been in the industry? When did I start learning graphics programming? It's really interesting to know. So I have been in the industry, as in I have been professionally doing this for um, um, hold on. I'm counting years. I think for 12 or 13 years, I forget. But I have been doing this as a hobby for like 5 years before this or so, doing custom engines, things like that, right? And I guess this is when I started learning graphics programming. So I started learning graphics programming, I think, when I was in ninth grade or something. I'm not sure what is that, what, like 14 years old or something like this. This was in the era of Direct 3D5, Windows NT, like actual NT, like NT4 or whatever, like retained mode Direct 3D and things like that, and OpenGL and Nehi, is it called Nehi OpenGL tutorials? Yeah, this takes me back. And also direct draw. So I did a lot of 2D stuff, not a lot, but like some amount of 2D stuff. Like I wrote a Diablo clone back in the day, long time ago. So, but yeah, that's about when I started. Since the 80s. No, I'm not that old, fortunately, or I don't know. Hello from Nepal. Hello. Have not been to Nepal, but I actually was in India this just recently, like a few, basically last month. It was really interesting. I'm gonna be back at some point. Any tips for new people trying to get into the graphics industry? Does it matter greatly what graphics API you know? If what would you recommend? So that's a good question. I don't have super specific tips, but I can outline in general the way I think about this. Redbearded Joe, thank you for your valiant efforts. I now can just not stress about this. Like, seriously, thank you. This was really bothering me when it started, because I really didn't expect this. So, there's many different areas that a graphics engineer can be proficient at, right? And so, didn't Angelo... Let me actually, hold on. I think Angelo had a really good post about this. Let me just see. We talk, Angelo works at Roblox, and we talk a lot about things like this, and we share a lot of views. Let's see. I don't see the exact thing I was thinking of. Maybe it's in the text somewhere, but alright, so here's how I think about this. Let me switch to this. You know these, like, I watch a lot of anime these days. There's this cliche, I don't know if it's extends outside of the Japanese culture, where you have like a car. Oh my god! Wow, this is not the right size. You have like a character card, and maybe this is not even coming from that. I'm not sure where this is coming from. Where there's like a photo, right? And then there is this star where there is this axis, right, of proficiency, and like an anime it would be like strength or whatever, or like ability to learn, and then there's this diagram, right, where it's like you're strong here, you're weak here, etc. I think there's an official name for this, I forget what it's called. And then you draw this chart, right? You connect these and then you shade this, and kind of the more area you have, the better you are overall, right? And so this is exactly how I think it's right to think about graphics programming. So there are these axes that they're not orthogonal, right? But to a certain extent they are independent. So one of them is, I think, graphics APIs, but also I usually bundle, but let's just call this API and I'll expand on this. Then the other might be performance, just ability to optimize. The other might be, let's just call it modeling, and what I mean by this is BRDFs, being able to understand the rendering equation parts of this, the irradiance, radiance, lumens, like all of this, like how do you think about the optics that go into the rendering of the world, right? So like it's a relatively deep, all of these are pretty deep. And then there are some others that you can think of, like there's geometry, which is what are the different ways how you can construct the geometry. I kind of bundle SDFs and other implicit representation into this, meshes, subdifs, how do you do tessellation, how does workflow work, how do you work with this as an artist, etc. And there's probably some other, there's like, it depends on, there's not a really fixed set of these, right? So in interviews, when people come and want to work for Roblox, I usually try to figure out for each of these axes how deep is your understanding. So for example, for APIs, it's not just about do you know OpenGL? Oh, what does this call in OpenGL do? I never ask these questions. It's more like how deep is your API background? How many different APIs do you know? For each API, do you understand why it's structured the way it is? Do you understand why in Vulkan the kind of resource bindings to the shaders is using the descriptor set model, whereas in DX12 there's a root descriptor signature and then there's like descriptor bindings to that? Do you understand what the driver will do? Do you have a conceptual model of, oh, I have VK, CMD, like bind pipeline, right? What does this translate to? Not like exactly, but what would the driver do to this, right? In different cases, what are the possibilities? On the performance front, it's not just can you optimize code, but how deep is your understanding of the GPU and CPU performance? Do you understand what drives the GPU performance? Do I understand how to profile this? Do I understand what are the ways to, how does hardware work and what are the ways to exploit hardware into doing what you need to do? Like, and you can ask a lot of basic questions to probe the understanding on this. Like in the performance kind of front is, hey, I have a branch in my shader. What are the performance consequences of this? And this is a kind of deep topic because it goes into a lot of details. And then it's like you can ask, well, if I have a branch that hits 90% of the time, can I make it faster? And then if a candidate knows some more modern features of modern APIs such as Vulkan subgroups, then the answer is yes. And if not, then the answer is I don't know. So for all of these categories, you can evaluate the understanding, the depth of the understanding. And it is not the case that every graphics engineer has to be like 100% on all of this. In fact, it's impractical. The hope, like for really good people, it usually is the case that there's one or two categories that they excel at. They're like better than most other people in the world at this, or whatever your benchmark is, right? But then in other categories they have some understanding. Like if you're zero in any one category, it's probably not that good for you because there's some overlap between them. And if you have some understanding of geometry, it's going to be easier for you to do modeling. And if you have some understanding of performance, it's going to be easier for you to do modeling in practice. And if you have some understanding of modeling, it's going to be easier for you to understand when you work on performance, how can you morph the solution to run faster at minimal quality loss, things like that. So getting back to the original question, right, which I already forgot, like does it matter greatly what graphics APIs you know? Well, it doesn't really matter as much if you know, for example, both DX12 and Vulkan, because they're the same class of API. If you know Vulkan, it's much better than not knowing any low-level APIs, because that shows two things. One is it shows that you are starting to understand how the GPUs and drivers actually work, because the driver expands much more API kind of surface area. Sorry, yeah, not API surface area, but like the API that the API that Vulkan gives to you is more low level, which means that you have to understand more precisely concepts like synchronization, etc. And then the other one is you are willing to learn, right? Like nobody forced you to learn Vulkan. You could have learned OpenGL, which is much easier, but you went ahead and did that, which makes it more likely that you're like curious, you're looking to grow yourself as a professional, etc., etc. So, if you are learning Vulkan, it's a pretty good graphics API. I'm not like in love with this with the API, but it is a pretty good API. And more importantly, if you really learn the API, and when I say really learn, this really means one thing. For different parts of the Vulkan API, A, how do you use them in practice? B, why are they this way, right? I keep hammering on this point. This is really important to me. When I work with people, I really want them to know not just how the thing works, but why does it work like this? Because that again shows the depth of understanding. So the deeper you go into this, the better you're going to be as a professional. But to my earlier point, don't exclude all of the other areas, right? Like, it doesn't say, oh, the API is the most important thing. No, it's not. It is important for some types of work, but other areas are also important. I don't really have really concrete advice, right? I think if you're trying to get into the industry, it's valuable for you to look at kind of various research topics that people are exploring, look at different code samples, try to understand how they work. Try to write your own renderer with a simple API, like try to write a deferred shading renderer, try to run a cluster forward renderer, try to play with some other special effects. Try to profile, right? Try to use vendor profiling tools like NVIDIA Nsight, etc., to understand how the performance of the code that you're writing works, right, and try to optimize it. Try to learn a different graphics API. The more things like this you do, the better you're going to be at this, and the higher it is the chance that you can break into the industry. And kind of that's the best advice I can give, right? I don't have I don't think there's a recipe that says do this, do that, okay, you're good, you're hired, right? DX12 versus Vulkan, which one would I prefer? So, I mean, I kind of am emotionally invested in Vulkan, in the sense that I spent a lot of time working with Vulkan, doing streams. I have a library that a Volk, which is like a loader for Vulkan, etc., etc. Generally speaking, I like Vulkan more. There are aspects of the API that I like more in Direct3D12. I think they are easier to use, I think they are better designed, etc. At the same time, I think I know why Vulkan is designed the way it is, and some of these reasons I can emphasize with. So overall, I like Vulkan a bit more. If you are learning for the sake of learning, like the thing I was talking earlier about expanding your horizons, it's fine to learn just one, and the other one will come naturally if you need this. Vulkan is probably better to learn because Vulkan gives you the opportunity to experiment with different extensions ahead of time, right? It's like you could experiment with NVIDIA mesh shaders before extensions. Ray tracing capabilities, I think, were slightly wider in NVIDIA's extension, but fundamentally it doesn't truly matter. If you want to learn DX12, it's also a fantastic API, and it will give you much better understanding of how the stack works, and you should learn that. Would I think about learning computer graphics without going to university? Is it a good time to mention this? I rarely, yeah, I mean, I never, if people ask, I never hesitate to tell them. I don't like make a thing out of this, but I actually don't have a degree. I dropped out of the university after the second year. So it was like a master's program, and then I studied for 2 years. And then I realized an important thing. So after my first year, and this is not, I'm trying to be careful about this because you shouldn't infer that you should just drop out and you're gonna be in an amazing place. But like, I'm assuming everybody who's watching this is gonna be able to decide for themselves what's the right path for them. So I just wanna say what it was like for me. After my first year, so I was doing a lot of kind of programming and graphics programming and stuff like this in my spare time and in high school. And then when I got to the university, I was doing this for the first year. And then I talked to a friend, and he's like, we want a job because we have a company and the company needs people, and you seem pretty smart, and maybe you should work for us. And I'm like, sure, why not? I mean, I don't know. And I joined the company, and I started working there, and I loved every minute of this. Just as much as I loved the kind of spare time experiments that I was doing, but this time it was actually necessary to ship a product. It wasn't just, oh, I'm playing around. It's like, no, it's like you're doing real stuff. And so I realized that I feel really happy at work and I feel really unhappy at the university because the university is forcing me to learn things that I wouldn't want to learn necessarily otherwise, and not teaching me things that I really want to learn. And so if I am learning, I have to learn myself. But then I have this mental pressure of, oh, there's exams and you have to prepare to exams. And some of the exams are fine. I just know all of the stuff. I just do them. But some of them require a lot of preparation, a lot of stress. And I just hated this. And I just loved the work. So I kind of took a leap. I said, well, and everybody told me, no, like you should not do this because in our society you're expected to have a degree. But doesn't I think John Carmack is also a college dropout. So people were telling me like it's gonna be harder to get a job. People were telling me it's gonna be hard to immigrate. I was in Russia. My parents were very correctly, I think, but I didn't quite realize this at the time, pushing me that my future is not in the country that I'm born. But it's going to be really, really hard for you to immigrate without a degree, right? Because you have to find a job. There are some immigration rules about having degrees, stuff like this. And I took a leap of faith. I thought, well, I really hate this. I really don't want to do this anymore. I'm gonna take the leap of faith and I am gonna hope that I can figure it out. And I did. I've been in the US for like 7 years. I don't have a finished degree. I have, I got like a visa that it's O1, you can like Google it later. But the way I got it is I dropped out, cool. I worked, but also I dedicated a lot of time to self-improvement, right? I had a blog, I did talks at conferences, at local conferences. I think I did like 3 talks at Russian Game Developer Conference while it was still a thing. I wrote like a book chapter, etc., etc. So what you can't do is you can't drop out because you just can't take it anymore, but you don't have a plan. I think that's a bad strategy. But if you have a drive, if you know exactly what you want to do in the future, if you have this passion for improving yourself and demonstrating your abilities to the world, it's probably going to be fine. It was fine for me, it was fine for Carmack. I know a lot of other people who went through similar things, right? But if you aren't sure, you should finish college, right, or university, or whatever it is you are enrolled in. How has my experience been with the Oculus Quest? I love Quest. Quest is super cool. The problem with Quest is there's like one game that I play on this more. There's like one or two games. The main one is Beat Saber. It's really neat. I was doing VR. We were doing VR in Roblox, and I kind of got into this, and I did. I played with the devices available at the time. We did an integration into the engine. I did performance optimization. I wrote a custom cardboard, was big at the time, and I tried to use Cardboard SDK. Cardboard SDK was bad, so I wrote my own, which was better. But then we never shipped any of this because like it's mobile, it's bad whatever you do. So I didn't really think it was possible to have a standalone device, which is the easier part, with no external equipment, track as well as Quest does. The hand tracking in Oculus Quest is exceptional. I've never felt like it was doing kind of something wrong. The hand tracking is not as good. The hand tracking, not the hand, sorry, the controller tracking. They now have hand tracking, which I haven't played with. I'm kind of excited to try this. I haven't used Quest for like a week now, and I think they shipped it middle of this week. So controller tracking is not as good, but like I know why. I talk to people who do this. It's a hard problem. It's a hard optical kind of optics, not optics, like it's kind of computer vision problem. There is complicated room setups. There is like a bright light occasionally in your room, or there is like a mirror which is just really hard to deal with and things like that. But it's really impressive. So I think what Oculus Quest needs, which VR needs as a whole, is a set of really compelling experiences. Right now, Beat Saber for me is really compelling. It's really cool. You kind of get into this. It's amazing. There's a couple of other games that I like on Quest, but they have shortcomings, and there is not this strong library of really compelling content, right? I want a game that I can look forward to playing next day, right? And then the day after, and then the day after, and then the day after. So I think it's not quite there from this perspective. But I think the Quest track is like really promising. I'm hoping that they can basically backfill the content, make tracking even better, maybe ship a next gen device with like more power or something like this. Like I don't know. I think it's gonna be good. I think they're on the right track. Dun 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 dun. Oh, just to finish on the whole college stuff. Right, the person who's asking this says they're in Nepal and there are no game companies that are local, so that's gonna be tough, right? I don't know honestly how it is in Nepal. All of these rules differ per country, etc. So I can't give like a contextual specific advice, right? I just said how it was for me. The generally speaking, it's going to be much easier for you if you can get a job locally and then figure it out, as opposed to trying to get a job with no prior experience in a specialized field like computer graphics somewhere else, outside of your country, etc., outside of your hometown. That's going to be harder. So it depends on, right, it kind of depends on what you want from life. So yeah, it's hard for me to, again, I'm trying to be really careful. Like I can't tell you what to do, right? You have to decide for yourself. For me, it was fine. It worked out. It allowed me to balance my time the way I thought was appropriate, but I knew exactly what I need to do. And I had a really strong internal drive, and still do, for being better, for making better things and stuff like that. What is the typed Lua beta? I don't know if it's the right stream. It's actually a fine stream to ask this. This is not exclusive to graphics. So yeah, for people who don't know, we've been doing a lot of work on Lua at Roblox in the last year or so. There's kind of two efforts to this. One is faster Lua, and one is typed Lua. And they're all kind of combined in the project we call Luau. So faster Lua is shipped. We rebuilt the interpreter basically from scratch. Did a lot of optimizations on various things. We are running on par for most workloads we've tested with Lua JIT in the interpreted mode, which, trust me, is a big achievement if you haven't looked in the space. We're running like faster than JavaScript's interpreters, not JavaScript JITs. There is an eventual possibility that there's going to be a JIT. So that's how the stack eventually might look like. The typed portion goes like this. If you write a Lua program, it's a dynamically typed language. So you can say, oh, I have function foo. My handwriting is pretty terrible, but hey, you have to bear with me. And then you say like print v plus 5, and then you say foo hello, or foo nil, or whatever the case may be, and then, you know, the code compiles, and then it runs, and then it errors, right? You cannot add hello to 5. Actually, you can add hello to 5, so that's a bad example, but you really shouldn't add hello to 5. Turns out, once you write a lot of Lua code, it's really hard to write correct code when the compiler doesn't check types for you, because this type of code can be subtle, it can be under branches, it can be in places of the code that don't normally run, but you have an amazing achievement in game that you haven't fully tested, and then you press a button and then you get a type error, and it feels really bad because, hey, shouldn't it be possible to know? And so we are working on the type system for Lua. The way this works is that in I don't recall what we will do in the specific example, but roughly speaking, you will be able to say there is a mode, for example, where the type checker has to know every single type, which is called strict mode. And so in this mode, I think this program might not compile, or maybe it compiles and we infer the type. But like if you say v colon number, then this line will have a compilation. It's sort of still a warning, but you can think of it as an error that says, hey, the types mismatch. And so this helps you build correct programs, right? This helps you have a lot of code in Lua that you type check and you're actually sure that it works. And we are building this in a way where if you have an existing large Lua code base, which a lot of our developers have and we have, it still works. And you can take a small module and type annotate it or enable typing for this or whatever. And then within that module, you're going to have guaranteed correctness. And then at the boundary, you might start getting warnings, but the rest of the program you don't have to touch and everything still works. And so this is called gradual typing. And this means that you can gradually introduce types into your program at your own pace and stop whenever you want if you feel like, you know, this piece of code, I really have tested this well, I don't want to touch it, it's fine, just leave it as is. It will work like this. So we were hoping to ship a beta this year. We missed the beta by like a week, which happened with a few other projects. It's kind of unfortunate. We have this code cutoff rule that is like a very good rule, which says, hey, a couple of weeks before Christmas, we stop shipping code. Because if you ship code with long-lasting effects, then this may result in on Christmas something goes down and then there's an emergency and then it's bad for our users and it's bad for us because we have to, you know, get from our Christmas vacation to like, hey, we need to fix production. But yeah, we couldn't quite ship it in time, but we are gonna ship a first early preview in January. And then the hope is that in the first half of next year, basically, there's going to be a very complete release that's basically good enough for like 80-90% of code. And then we are going to expand on this in the future. So that's what's going on in the Lua land. Oh, that's a fantastic question. What are some things that I do that have helped you keep your high performance work routine maintainable for so long? Don't you get burned out? Two things. One is Jonathan Blow, that was mentioned in the stream, has a really, really good talk about, I think, malaise, it's called. I kind of recommend watching this just in general. I didn't like again, I don't think about this again as exactly as he does, but and I don't have a very strong as strong of a mental model as he does. So you should watch this his talk, and maybe that will give you good ideas. For me, the big thing that I try to do is I try to diversify the work that I do. Somebody actually there's a segue. Uh, there is a segue that I heard. There's a question right after this, which is what is my favorite challenge to tackle in the recent memory? And so my favorite challenge to tackle in the recent memory is actually the fast Lua implementation that I did, like the faster VM. It's really, really tough engineering problem. There's like a lot of really deep stuff that I wanted to try before but never had a chance to, and that was super cool. I was really happy doing this work. But I haven't done language programming in a while, and I haven't, generally speaking, done it professionally, short of something I did at Roblox like 4 years ago. So, and last time I did the language programming personally, I did this a couple of years ago, and I kind of burned out slightly at the end of this, which means doesn't mean I got burnt out in the real sense necessarily, but I kind of, well, maybe it's the same thing. I started feeling like, yeah, I'm playing with this language stuff. I'm kind of getting bored of this. I don't feel happy doing this. If I push myself to do this further, I'm gonna start hating what I do. So I stopped doing that, but I started doing something else, right? And I think at roughly the same time the Mesh Optimizer was born or so. So I try to say, hey, what's the thing that really interests me in the technology space right now? Can I work on this? How can I work on this? Roblox is a fantastic company to work for in that sense, because if I decide I'm kind of getting bored on graphics, which actually happens to me, I haven't really done serious graphics work in the last year or two. In fact, at the beginning of this year, or maybe earlier, I kind of sort of promised people Vulkan streams about RTX, and then I tweeted about this. I thought about it, and I'm like, I really don't feel like doing this. I am kind of burned out on Vulkan, right? I'm burned out on graphics. But I feel really happy doing other types of work, right? I feel really happy doing physics work or language work or computational geometry work or whatever. And so my strategy for dealing with this is take the thing that I'm passionate about right now, do that. Do it sustainably. I used to have severe problems around, and I sort of still do, about like work-life balance thing, right? Where it's like, oh, it's so tempting. You're in the middle of this. It's so good. You're pushing yourself to get it done. You feel awesome. There's this adrenaline rush, and then you're just exhausted at the end, and then you're just done. And so I try to manage my time to have this not happen, but also, what is my passion right now? Can I execute on this? Once I'm done, should I work on it further? Or am I getting tired of this? And is there a risk that if I work further on this, I'm gonna get burned out completely? Like to the point where I will feel pain getting back to this topic, and this is what I don't want to happen. So I try to leave like before that happens and switch to a different thing, right? And so this is why I haven't been doing graphics seriously for the last year or two. The other reason is, I mean, at work, we hired a lot of great people who are really, really, really well equipped to do graphics instead of me. And but the work that I'm doing now with like GLTF and stuff like this, it's in a similar field. It's just different, right? So I feel like even inside a field that is wide enough, such as graphics, you can try to navigate this space and sort of look in this direction, try going there. Okay, you feel kind of like it's not the thing anymore. Okay, go in a different place. I haven't ever been completely burned out from programming, honestly. I programmed pretty. I mean, I don't. I haven't programmed every day, but I've programmed like, oh, definitely every week, for many years of my life now, right? Since I don't know. It could be for the last yeah, definitely 15 years, maybe slightly more. Not every week necessarily, but like frequently, right? So I can't give you advice on that because it has never happened to me that I've just completely been burned out on technology, right? And so I don't know if this is because I am able to successfully navigate the space, or if it's just because I'm wired differently and technology is so core to me that I don't, like, it doesn't happen to me. But I heard people say it's a dangerous like route, in the sense that, yeah, you feel like, yeah, technology is your core thing, there's no way you're gonna get burned out, and then you get burned out, and then it's like, okay, I'm done. So yeah, but that's my strategy. Try to follow my passion and try to jump off my current passion when it becomes kind of weak for me, to something else that's new and important and complicated, and navigate this like this, so that every time I do this, I am doing new things, I'm learning something new, I have new challenges to solve, and I don't feel like, oh, you're just wearing me out. Hello from SPB. I'm assuming that means St. Petersburg. I haven't been to St. Petersburg in 2 years, but hello, and hope it's as lovely as it ever was and is. Any good sources to implement volumetric lighting? I don't. So my recollection is that Bart Ronsky has a really good blog on volumetrics that may help you. But that's my just most recent memory. Let's see. Can I find this? Oh, maybe I should use Google to find this. Yeah, this is what I'm thinking of. So it's not quite, I guess. It's sort of similar to what you're asking. Maybe, let's see. Oh, is that really what I am thinking? Yeah, this thing. So this is a really good resource. It really helped me get a better understanding of different approaches to work with volumetrics in the past. Maybe there are some other canonical references that I'm not thinking of right now, but I would try to watch, look at this. I'm not sure if there's a video. Look through the slides. If it has references, try to read references. I don't have like an implementation tutorial for you. I usually don't read these, or don't consider them as valuable as deep presentations like this. So, what's my opinion on BCI? What is, sorry, I don't even know what the abbreviation is. BCI for their platform, a device that acts like a creativity neuroprosthetic. Huh. This is probably completely outside of my area of, like, see, I don't even know what these words. Well, I know neuroprosthetics, but I don't know anything about this. Any thoughts on machine learning in computer graphics? Huh. Interesting. Any thoughts on machine learning in computer graphics? So, it's kind of interesting. So I think machine learning in computer graphics has a couple of interesting applications. One is offline procedural generation, content cleanup, things like that. I think there is a lot of promise, and there's some research in some areas that seems promising and fruitful, and I'm kind of excited to see where it goes. I'm not an expert on machine learning. I've been trying to get some solid chunk of time to dedicate to this, but kind of just doesn't fit with my schedule right now. Maybe once Mesh Optimizer gets to like a really good place in terms of the projects that I talked about, I can do that. But so that part I feel really kind of solid about. Like, I think it's good, from my understanding. There's another part which is like real time. People talked about, hey, can you do denoise, right, using ML? And you can. can you do various post effects using ML? There is a paper that I probably will not be able to find about SSAO, like screen space ambient occlusion, using machine learning. I'm like really cautiously, I don't even know if I'm cautiously optimistic, I'm just cautious about this stuff in general. My big, and part of this is just I don't have a strong background in machine learning, so I don't have the right intuition for what things work, what things don't. But my wariness comes from two parts, right? One is you are taking the human out of the equation kind of early, in the sense that for SSAO, I think the way they train the network is they ran a bunch of SSAO implementations, and then they ran some like ground truth stuff, like ray traced AO and stuff like that, and then they fed this to the network, and then they said, hey, like train on this, right? And then they run inference to actually do the effect. So it's cool and all, but I feel like you're removing the understanding of the algorithm from the solution. And so what worries me about approaches like this is that then you're not able to find really creative solutions that you wouldn't have thought of otherwise, because you don't truly understand the problem that you are solving. You're kind of hoping that the algorithm will do this for you. And in some areas, I think the humanity has mostly given up on like understanding the problem, right? Like if you think of machine translation, there's a long history of trying to do machine translation for real. For real is not the right term, but like based on the understanding of how different languages are structured and specific solutions for specific languages and stuff like that. And to my knowledge, a lot of the progress in the recent years has been around skewing a lot of this research and just saying machine learning. It's not just like I'm. If anybody who is watching this is actually a machine learning expert, they probably like he doesn't know what he's talking about, and this is true to an extent. But you are changing you instead of solving the problem, you're kind of solving the meta problem, which is a bit of a different type of solution and type of understanding. So yeah, I'm not like super comfortable with this. And the other part of this is that you look at these networks and some of them are just not very fast to inference. And then you don't know what to do with this because you can't really reason about what the network is doing. So you can train a smaller, like you can like reduce matrices in the later layers or whatever, and then your inference solution runs faster. Or you can optimize the inference framework, but like you don't have like a core understanding of how the thing works. So you can't have a solution that runs in like 1/10 of the time, but gives you like 90% of the quality. And that I feel is what real-time computer graphics has been about. Like finding creative solutions that run in very, very little time that still get you close enough to the ground truth. And so I'm really cautious about this. Having said this, machine learning is a kind of is a umbrella term, right? What I'm talking about right now is mostly neural networks, but actually it's an umbrella term. And so there are areas where I think we should do more machine learning as a discipline for sure in graphics. And there's examples of this. There's one example actually in Roblox, which is our PBR solution uses GGX with some tweaks and stuff like this, but we don't compute GGX at runtime. Angelo Pesca did a lot of this work, and we have another engineer, Bonnie, who did like the other part of this. And so they collaborated to basically say, hey, can we run the ground truth simulation on the real formula that we are trying to compute? Can we experiment with different types of approximation formulas and fit the coefficients so that the resulting formula is still close to the true solution, like GGX, right? But doesn't take as much time to compute. And this is what this is because we have unique constraints, like we have this physically grounded BRDF that we want to run on low-end mobile devices, and like how do you do that? And so this is how we did this, right? And I think this is a really, really interesting way of doing this, where there's some amount, this combines this for me fixes this problem, because you're saying, well, I have a thing I'm trying to approximate. I need to take a guess as to what the shape of the approximation looks like as a human. And then I'm gonna use fitting basically to fit that to the like formula that I'm trying to approximate. And there's another example of this in Mesh Optimizer actually, which I'm going to write a blog about, so I'm not going to talk about this too much. But so I think machine learning as a discipline is something that we should use way more of. In terms of using like neural networks directly to solve problems, I am optimistic in some areas and like cautious in some other areas. I'll be starting full-time in Roblox in 2020, but I'm concerned about getting locked into one job and not being able to move throughout the company. In Roblox, in general, we have internal transfers that are basically frictionless. We have people who have moved the areas like many times. We have an engineer who used to work on one team and then decided they want to do something else, and then decided they want to do something else, and now they decided just recently that they want to do something else, and so they switched like 4 teams. We have somebody who's worked at Roblox for a while and they switched like 7 teams. Follow your passion. I don't think there are going to be any internal barriers at Roblox to block you from that. And also, when you start in 2020, come and say hi. Is there anything I can talk about yet in terms of multi-threading for WoW? Yeah, we I gave, I think it was the same question at the end of my RDC talk, if I remember right, and I gave a non-committal answer, and I can't give a different answer. I don't have a super specific one. Like, we are starting to, I think we have a couple of different models that we are talking about that feel practical, but there's probably going to be a progressive rollout in terms of there's a thing we can do that we know is safe, we are comfortable doing this, we think it's too restrictive in terms of developers being able to actually use this. There's a next thing which we think is going to be much less restrictive, and we think probably we can pull it off in terms of being safe and all, but we aren't sure. The proof is in the pudding. And then there's the thing after this, which is if that's like a leap of faith, like maybe we can figure out a few central pieces of the engine and restructure them in a way that you can do a lot of like most of the things that you can do today from a multi-threaded context, but that's like far out there in the sense that we have to ship this solution first for the more restrictive applications and then figure it out. So yeah, no concrete details yet. How do you guys decide how much time to spend prototyping soon TM technology compared to upgrading existing tech or developing soon to release new client studio features? So, I mean, there's no like rule to that. There's no process that's like official process for this. It's an art form, right? Yeah, I don't really know how to explain this, because honestly it kind of happens. Like, people who've been here for a while have a general sense of which areas of the engine are weak and which areas of the engine are strong, but also which areas of the engine should take a quantum leap and like just be, there's like this completely new thing out there that's just it's gonna take us forever, but it'll bring us to the new level, versus somebody just needs to work on this and improve this, right? And so it's a balancing act where you look at what are the big things we want to do in 5 years. Which of these big things we think are A, really impactful, B, have a slice of them that we can ship in like a year, right? And if we find something like this, then we start working on this. If for a specific area we think it's like a really cool thing to have in the future, but we don't have solid ideas right now, then we are kind of waiting for the right moment. So for example, real-time global elimination is something we want to have at some point in the future. we have had some internal prototypes. I did something on Hack Week a few years ago. We've talked about some things internally, but none of them are like slam dunk promising, right? It's like, oh my god, if we only could have this, this would be great. Then I'm like, yeah, like you wrote code does something neat, cool story. I'm not really excited, right? So this means we are not ready to know if we can do this yet. This means I think we are waiting for the right moment. For every technology that we do, there is the right moment in time to do this. And some things are very premature. I think my future's bright stuff was really premature, as is obvious by us taking years to ship this fully. Which, if you can do something that looks several years in the future over a span of Hack Week, you should absolutely do. But it just means that it's hard to commit to this without doing this prototype experiment. So yeah, for everything that we do, there is the right moment. So it's hard to know, like, I can't give you a recipe, right? The way this happens is somebody comes up with an idea, and then we look at the idea and we're like, it's really interesting, we have no idea how to do this. Or, there's actually a really neat small slice of this idea that we think is practical. Or, hey, you had an idea, you made a prototype on Hack Week, it's amazing, how do we get this, right? So this is kind of how we manage long-term stuff. And short-term stuff is easier. It's just that like there are some things we know we need to do. In some cases there are projects that require certain tech, so we know we have to get this done. In some cases there's just an obvious gap in technology, and we talked about this internally, and it's like, okay, hey, it seems reasonably simple for us to do, so let's just do this. There's a few pieces of tech that we do that have disproportionate impact, and these are really hard to find, as in the amount of effort spent on the project is disproportionately smaller than the amount of benefit that we get from this. Two examples from recent memory are surface GUIs and beams. Surface GUIs were like a thing that we talked about occasionally. It's like, yeah, does anybody want this? It's like and it's kind of weird. It's like it's taking this system that's built for 2D, it's kind of trying to integrate it into 3D. And then at some point we said, well, it feels like it's actually like a project that takes an engineer 3 weeks to do. Can we just do that? Let's just do that. And then we did this, and then, every game uses them. And beams were similar, where beams were not even on the radar. And then I forget how they came up, but I suspect that the engineer who implemented this just said, hey, why do we not have this? Can I just do that? And then she did, and then a lot of games use beams, and a lot of them use them really creatively, right? So things like that are just hard to find. It's like sometimes we discover an idea and we implement the idea, and it turns out, oh my god, we should have done this earlier. There's no process for this, it's art form. Besides the acronym for brain-computer interfacing, yeah, I have no idea about this stuff. I'm generally speaking not a hardware person. I'm like a software person. I go to the software-hardware boundary and I try to take one step further, but it's hard for me to take many steps further. So I usually don't know much about this stuff. Where I am in this? Oh, Google Metrics is from Sebastian Hilaire. Yeah, probably. I know Sebastian Hilaire. I just didn't associate specifically his name with this, but yeah, as you can tell, I am not necessarily an expert on some of this stuff, right? I'm not an expert in volumetrics in particular, but in general, you should read the research that Sebastian does, because a lot of this is really good. So. I tried Roblox the first time last year, was surprised that it requires an installer, expected more like web interface, login and play thing. Would it be technically possible, useful? Yeah, it's technically possible. We talked about this over the many years and never did, and I'm kind of happy we didn't do that. So you can, and definitely web in general supports this kind of capabilities, right? You can compile a code base to WebAssembly these days, as ASM.js before, can run it. There's two things about this. One is the stack is evolving rapidly and you're on the bleeding edge all the time. WebAssembly is relatively new. ASM.js is kind of like it didn't prove, like people were hoping that it would scale to large code bases and it didn't. In WebAssembly land, in general in browser land, so there's no CMD. And there is now almost CMD, but not quite. And there's threads, but they aren't always enabled in all browsers. And like when Spectre meltdown drama happened last year, all browsers deactivated threading. So if you had an application that ran multi-threaded workloads on the web using shared memory, so like you have a C++ application, you compile it to WebAssembly and stuff, you would just lose threading. And like, can you build a business on top of this? Can you build a business like Roblox on top of this, where we are really big? Like, if people here don't know what Roblox is, it's completely understandable because we have a special market segment. But also go to corp.roblox.com and like our business numbers are like insane, right? So like, can you build a business of our scale on something that like this that you don't control? But the other part of this is, also, there's still no UDP networking, and I don't think it's going to be a thing. So you have to use WebSockets, which is TCP, which had offline blocking, etc., etc. It's a problem. Or there is WebRTC, I think, which maybe is better, but it's a crutch. Anyway, there's like many limitations. You don't control the platform. But also, when we looked at this first time and second time, First time we had this discussion, I think was 5 or 6 years ago. Second time we had this discussion was 4 or 5 years ago. It just wasn't there, right? Like WebAssembly was not a thing, threading was not a thing, CMD wasn't even on the horizon, it was slow, it just wasn't there. And in some ways it still isn't. I think you can build convincing demos today. I don't think you can run a business. And when you do build a convincing demo and expect consumers to use this, well, you're compromising their experience, because WebAssembly CPU code, WebAssembly is cool, I like it. WebAssembly CPU code has, in my experience, roughly a 2x performance penalty, assuming the C++ code you are starting from does not use CMD, does not use threads. If it does use CMD, you're looking at a giant generational leap. Threading, I think, is probably fine now. If you use GPU, you're restricted to WebGL 1. Some browsers support WebGL 2, not all of them do. Even WebGL 2 is like OpenGL ES3, so you want to run compute shaders. Well, there's sort of maybe a way to do this through some extensions that like one browser supports in experimental mode, but not really. So as a consumer, your experience is bad. So the only thing you're gaining is the reduction of friction. Reduction of friction is important for first-time users. Like, I don't know what the thing is, I want to click play, oh, hey, it's cool. We used to be really worried about this many years ago. We aren't anymore. We are not in a position anymore where it's really critical for us, for new people to learn about Roblox and want to try it for the first time, but they click on the button and they have an executable and they are scared and they go away. It's not a problem. Having said this, we try to make our installer flow as smooth as possible. There's no distributables, there's no DLLs, etc., etc., etc. It's just like executable, you run it, it installs, you run the thing. And the flow will become even smoother in the future. We have some plans for this for next couple of years. So just basically, when we talked about this first, it made sense for us as a business, but web wasn't ready. Today, web still doesn't feel quite ready, and it doesn't make sense for us anymore. My particle system is GPU driven and rendered using geometry shader, transform feedback and texture buffers. How to store particles in GPU memory by depth for correct alpha blending using OpenGL 3.3. Oh my. So I'm struggling. I haven't personally solved this problem on the GPU before. I know the classical solutions are like Bitonic sort, etc., but most implementations that I have seen for Bitonic sort don't fit in GL 3.3. They require, I think, compute shaders and read-write buffers, where I think texture buffers are probably just read-only, and I guess you're using transform feedback to like circumvent this. So I suspect it's possible to do GL 3.3 sort. Maybe somebody has done this. I don't know off the top of my head how to do this. Like, I mean, your keywords are Bytonic sorts, so if somebody has done a Bytonic sort implementation of the GL 3.3, like, it's probably possible because Bytonic sort runs in passes, so you can probably implement each pass of Bytonic sort using transform feedback and stuff like this, but it's gonna be pretty painful. So yeah, is there a reason why you use GL 3.3? Can you use something more modern is my question, right? Like, if you are trying, I feel like in general, if you are trying to explore GPU compute, you should try to stay a bit ahead, and you should try to use an API that has geometry shaders, read-write buffers, read-write textures. I mean, basically that's it, which in practice means Direct3D 11, or I think GL 4 point something, 4.5 probably, which is like the latest on Windows, right? Has this, or Metal on Apple, or Vulkan. That would be my general advice, but I think you can probably do this with GL 3.3. It's just got to be painful. So, like, do you want to do this? Nice of you answering questions, and wish you happy holidays. Thank you. Have a good day as well. Are you participating in Hack Week this time? Yes. Stadia for easy try. Can't really comment on this, but yeah, maybe. Are you satisfied with the behavior of the sound engine Roblox currently uses? No. So we actually have plans for this for next year, which is the first year where we are gonna, well, not the first year. We did some sound work like 4 years ago, so, but some of this was really good, but it's not enough, right? And then sound in general is unfortunately a neglected part of the engine. I think it's generally speaking true where sound tends to be neglected because, you know, like rendering is obvious, it's a pretty picture, and then all of the physics, gameplay stuff, like if your gameplay doesn't work without something, you should do something, and then audio tends to be like a third-class citizen, not even a second-class citizen, so not satisfied at all. We could do so much more work on audio. We haven't had honestly just like time to dedicate for this. Like, this needs somebody with deep audio experience, right? And who can work on this stuff. So we now have people like that, and they're gonna work on audio stuff next year, and I'm hoping that we'll have good progress on this. So not satisfied with current state, but we are gonna make this better. Compute shader plus indirect drawing. Well, right, so like for particle systems, you do need indirect drawing for the final thing, right? My point was that basically to do the actual sort, it's gonna be much easier to do this from a compute shader with read-write access versus transform feedback, which is like, I don't like transform feedback in general. Transform feedback is, right, so like, if you looked at the thing we talked about earlier, which is the, hey, raster pipeline is complicated and I need to wait. No. Oh my god, hold on. I need to unlock my Surface Pro because it went to sleep and something goes wrong. Alright, so we talked before about the geometry pipeline, right? Like the actual reality of this, it's even worse because also there is a transform feedback stage, or it's called stream output in Direct3D world, which can output the results of that stage. And cool, neat feature. The reason why this feature exists is because compute shaders were not available at the time. And people thought, well, hey, what if you could store the results of the pre-raster phase and then raster that later? And there's some good use cases of this. But today, most of this can be implemented with stream output with compute shaders instead of stream output and stuff. In fact, I'm really sad about this because, and people from Vulkan committee know this, but I mean, I think they did sort of, I understand the motivation, I just hate it. There is now an extension called VKEXT transform feedback. Oops. And the reason why it exists is nuts. And this maybe is going back to the Jonathan Blow talk because, yeah, like, I mean, it's a problem. I don't think it's quite as bad as he thinks it is, but why did it? Oh my god. Come on, Microsoft. I'm using this device. Don't go offline. The reason why it exists, of course, is because there is a thing called VK-D3D12, sorry, DXVK, which is actually part of Steam's Proton initiative or engine or whatever, which is good because it allows you to run Windows games on Linux, and I guess people who run Linux are happy because of this. But like, Direct3D12 has a feature called StreamOut, and some games use StreamOut. They could have used compute shaders instead, but it takes time to, like, nobody tells them not to use StreamOut, so they just use StreamOut is my guess, right? And like, it takes time to rework all of this code, etc. So they use StreamOut, and it's hard to emulate StreamOut efficiently. And GPU supports StreamOut, but Vulkan doesn't. And so now there's a Vulkan extension to support transform feedback, and I was hoping that transform feedback at least is this part of this complex geometry pipeline that can go die a quiet death without all of the mesh shader stuff, but no, like, it kind of came back. So yeah, I'm not a fan of StreamOut. It's like a legacy crush. You should use compute shaders. For GL 3.3 compute are supported. Yeah, that's probably right. I tend to be, so we used OpenGL a lot at Roblox, right? We never ran it. Well, at some point long time ago we ran it on Windows, but there used to be a point where every non-Windows platform basically was using OpenGL or OpenGLES, and we are trying to move away from this, and it's working. We use Vulkan on Android if we can. We use Metal on iOS and on macOS if we can. We use Direct3D on Windows, on Xbox. OpenGL is very, very large API. It's hard to reason about performance. It's not very pleasant to work. It's like great for some things, but it's not kind of the savior that everybody wanted it to be. And honestly, these days, if I had a choice, I would just not use it. I don't have a choice. I mean, we have to use it for some of the devices that don't support other APIs. But from the point of view of getting optimal performance, of having all of the features available so that you can use them efficiently, from being able to point of view of being able to reason, I talked about this before. This GL command, what does it actually do? GL is not a good API for this. So it was good while it lasted, but yeah. Alright, so we are getting close to the 2 hour mark, and I originally thought that this would be like roughly a 2 hour stream, but obviously depending on the questions that people ask and stuff like that. Anybody has final 1 or 2 questions that I can talk about? Maybe one really interesting question that I can talk about for 10 minutes and then we'll end this. I feel like in general this was a success. I didn't really know what I'm getting into because I've never done a thing like that. I just kind of felt the urge to stream, and I didn't feel an urge to program on stream. So I'm like, hey, let's try this. And we talked about some pretty interesting topics, I think, both on the actual kind of technology implementation front, but also meta technology, right? The career, the technology evolution, all of that. So, any really interesting questions or how feasible to be to implement these regenerated tags? Not really my domain. We talked about this. I don't know if I can. Let's just say it might happen. I mean, it seems like a good idea. It's just, as everything in tagging, you have to be careful. The history of SEO. Oh, that's a really fantastic question. The history of SEO, like search engine optimizations, tells us that you introduce tags because tags are easy and obvious, and then you have no mechanism to prevent tag abuse, and then everybody abuses tags, and then search engines stop using tags completely because they give you no signal. And so basically, if there are ways for us to do tags well so that you can't abuse them too much, then it seems like a great idea. We have some plans around this, but I can't really go into details, I don't think. Cool. So yeah, let's just so two questions. One is GPU usage by Roblox is really low even when frame rates are low. Is that due to poor utilization by Roblox engine, more likely to be something else? It's a bit complicated. It depends. Like there are some games where GPU usage is high. There are some games where GPU usage is low. In general, we tend to target lower end GPUs a bit more strongly than we target high end GPUs. So if you have a high end GPU, by necessity, we will be overutilizing the CPU, right? But the dynamics really depend on the specific game, the specific hardware, etc., etc. We have a general desire to push more high-end effects next year, and so GPU will have more load than it does right now. But it depends, right? Like, I don't think it's the case that we are utilizing the GPU poorly, in the sense that there are workloads that are really that run on the GPU but are really inefficient on the GPU. It's more of a balancing question. So yeah, the data is stored between graphics. Where is the data stored between graphics pipeline stages, between running vertex and geometry stages? So Redbearded Joy is feeling justifiably really proud. So that is a good question. The short answer is it's complicated, but also the longer answer is it's kind of why things like it's part of why geometry shaders are kind of hard to implement well. So the way this usually works on GPUs is like this, and the question is very, very apt. So so there is a vertex shader, right? And then there's a triangle. So there's 3 vertex shader invocations, and then there's a geometry shader that takes data from all 3 vertex shader outputs, right? And then does something with this, and then outputs 1 or more triangles. So let's say you have something where, what's a good example? Like one of the early examples of geometry shaders were fur, right? And to do fur, you have to do 2 things. One is you have to do extra triangle layers. So let's say you triplicate your triangle. So you output like 3 of them like this, and then you have a texture of them that looks like fur if you look from above. And also what you have to do is, it's called fins. So it's getting slightly, I'm just gonna draw one of them. You have a quad like this. So it's like 2 triangles. And on this quad you have a different texture, and this is so that if you look from the side, it also looks like fur, right? And this can look really, really nice and also be really expensive on the pixel shading front. But so this geometry shader outputs, let's say 3 triangles, like horizontally, vertically, whatever, like 3 triangles in this direction, and let's say for the simplicity it outputs 3 fins, right? So each fin is two triangles, so like 6 triangles for fins, 3 triangles for this, so like 9 triangles. Cool. If you write a CPU program, you just store, like you just run vertex shader 3 times, then you run geometry shader 1 time, then you get a bunch of triangles and you rasterize each one, right? But the actual reality is there is like many concurrently executing vertex shaders and geometry shaders. And so what usually happens is twofold. One is there is usually a short buffer on GPU that stores data that passes between different stages, and it's usually like a ring buffer, so it's FIFO, first in, first out. So vertex shader workloads, for vertex to geometry transfer, it's a bit complex. For geometry stuff, for example, if your geometry shader outputs like 2 triangles, then maybe it'll fit in FIFO, and there's just a FIFO that is really small where each thread can output 2 triangles that will go into that. This memory is on chip, so it's fast, and so this goes into raster, and this connection is like super fast. But then what happens if geometry shader outputs 9 triangles is, well, there's 2 problems. Like, one problem is you may not be able to afford many short FIFO buffers, so maybe you have to have one larger FIFO buffer, but then you have complex synchronization around what if there's no space in the FIFO buffer? Do you wait? Can you wait? It is, generally speaking, a really hard problem on the GPU, where you have to have this massive parallel engine, and you have to guarantee forward progress, and you have to finite hardware resources. So it's like, what happens if you have let's say 100 threads on the GPU, and that's like a constant finite number, and then all 100 of them, and this is like a very low number, but still, run a vertex shader workload, let's say, and there is no space for the vertex data for all of them. So you want to run the geometry shader to free up that space, but there is nowhere to run the geometry shader because you have all of the threads like busy. So you have to take some of them off, like pause some of them, but that's a really hard problem that is not always possible. So usually there is like a short buffer on chip for some stages, but like the actual reality is that in a lot of complex cases things don't fit, and then you use a large in-memory buffer. And so this is why, for example, in geometry shader world, there is a geometry shader, and there is what NVIDIA calls a pass-through geometry shader. I think it's called FastGS in NVAPI. I don't have space. FastGS. And what it does is it says, well, the geometry shader that doesn't multiply geometry and also has some other properties where it just forwards all of the vertex attributes directly to the rasterizer can run quickly. And the reason why it runs quickly is it doesn't have to store anything into memory. It's just processes the triangles and then feeds the result into the rasterizer without having to use the large memory buffers. So I think that's the general idea. What I would highly recommend you to do is Fabian Giesen trip through graphics pipeline is to read this blog series. There's 13 parts here that talk at length about possible implementations for different parts of the GPU pipeline on actual real GPUs, like what it does in practice. This is written in 2011, but as far as I know, a lot of this is to a large extent still true. Some of this might be different on some really modern architectures, like NVIDIA had some progress with on the compute front with like some thread basically for fork join that you have to do for branches that I think Fabian doesn't talk about because I think it didn't exist at the time, but it talks about geometry shaders at length. I forgot if it talks about the ring buffers. It talks about buffering. So this has probably much more accurate and much larger description of the kinds of problems that you have to solve for things like that. All right, let me briefly look at the rest. All right, I'm gonna answer a final question from Context Lost. Only because it's Context Lost and asking the question, and then we are gonna end the stream. And then it looks really, really nice out there, so I know what I'm gonna do. So any suggestions for working on a deeper understanding of low-level performance modern pipelines, debugging at the assembly level, anything that was particularly helpful for you, any recommended reading or ideas for practice projects? So the biggest thing that was helpful for me is twofold. One is one is theory, one is practice. So on the theory land, on the theory side, there's two things that I think will help. One is understanding how the process works on a deep level. There's two ways to gain this understanding. One is to read the architecture optimization manuals, which is actually like, so Intel has one, it's 600 pages, which is kind of long, but it's pretty readable. Like, it's not a, oh my god, there's this giant encyclopedia that I just completely can't get through. It's pretty readable, and it usually gets you a pretty solid understanding of like how things work. Intel optimization manual, I think it's called. Dun, 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 672 pages. But you don't have to read like the entire thing. like you can start reading this and then you can stop, or you can browse through the table of contents and kind of pick areas that interest you more. So that's good. The other thing that's good is there's a few nice. I'm trying to remember if I can just find like blog posts that talk about this nicely. Let's see if Fabian wrote something up. I feel like he must have, but I don't know. Fabian had a nice stream series, so he has a YouTube channel, to check that out. He had like a couple of long videos, like 3 hour plus, and then there's like 2 or 3 of them, where he talks about microarchitecture on the hardware level, and that I found for myself like really insightful. So yeah, let's see if this is good, but this is not as good. Not, it's good, but it was not exactly what I had in mind. So yeah, try reading the architecture manuals. They're pretty readable. Maybe that's good. But the other big thing is trying to optimize. So the way I gained understanding that I have, which is not very complete, but it's like reasonable, is by combination of reading things like instruction manuals and things like that, and profiling. And so the way you profile, the way I recommend you do this is get VTune. VTune has a free license now. Fortunately, after many years of VTune being like $800, I can't afford it as a hobbyist. There's now a free license, so download VTune. Try to find code that you wrote, find code somebody else wrote. Run VTune. Look at what VTune tells you. For each metric, there is some documentation in VTune, trying to understand what they do. This is why like you probably should read some of the architecture manual stuff first, because I think it talks about the front and back end division and instruction environment and things like that. But let's see. Maybe there's like separate, like I would generally speak in Google Intel front and back end, like instruction retirement. Maybe there's like an overview post for all of this stuff. So Intel VTune has some documentation on this, so maybe that's just the best way to do this. So run VTune. VTune will show you the assembly. VTune will show you which instructions take how much time, where are branch misprediction, stuff like that. And then try to experiment with different optimizations for your code, right? Like, for example, branches are complex. Like if you have a branch and you want to remove this branch, it's tempting to say your code will be faster because branch misprediction will not occur anymore. It's tempting to say your code will be slower because you'll do more work. And so the actual reality is complex and it depends on the kind of branch. So try to experiment with different things like that and just see kind of how they reflect in the actual performance profiles that you're getting. And then try to read the instruction manual to try to give you some background. Plus, for some specific things, it's like, oh, like there's a stall here because this instruction depends on this instruction, but like, why is it the case? Or the other useful resource, I'm assuming you're already aware of this, but Agner Fog has a good set of resources. The instruction table stuff is really awesome. Oh my god, what? Okay, I never go to Agner's front page. Instruction tables are good as encyclopedic reference. Like I wanna know, is integer division slow? I would recommend reading, I think I would mostly, if you want to read the other stuff, I think it was pretty good as well, but I think it's not as relevant to the topic. I would read this. I think this is shorter than the Intel's guide. Maybe you should read this first. So this is like a fantastic reference as well. And yeah, then just experiment, try to do different things. And on the assembly level, I think what is generally speaking just helpful is try to debug your code stepping through assembly instructions in release with optimizations enabled, which is going to give you a much better appreciation of kind of how the architecture, not how the architecture works, but like what is the ABI, what do the registers mean in different cases, how do I know where a local variable is in some complex cases. And I think Agner talks a bit about the ABI in some of this, maybe, or maybe not. Yeah, he has a separate document for ABI, which would be good to read. So maybe the useful strategy is read all of the Agner stuff. I think it's shorter, except for the instruction tables, which don't read the entire thing, just like look at it once to understand what it's about. And then try to read the Intel's thing. It's really long, but parts of this are really good. So and a lot of experimentation with software that you care about, right, and trying to optimize that. All right. Yeah, Agner's tables are like encyclopedia, right? But the other Agner's documents people usually don't accentuate. I don't think I've read all of them. I don't think I've read the assembly optimization guide or whatever, but I have read the microarchitecture introduction, and that was pretty good. And I think I've read the C++ stuff. I think his C++ stuff is slightly weaker because it mirrors the general advice about performance optimizations that you might have read before a bit closer. All right. Anyway, this was fun. I've been talking for 2 hours. I feel like I got what I wanted. I hope you guys got something useful out of the stream. The stream will be on YouTube. So if you want to come back to this or whatever, or people who didn't catch the beginning, caught the end, it's gonna be on YouTube. And also next time, if next time happens, which we'll see, this was like the last opportunity for me to do this stream this year, because final plug for Roblox, we are all going on vacation basically from 23rd, is it? Like the next week is Hack Week. And then the weeks after this is basically Christmas break, where basically the office is going to be closed. Insomniac did something like this as well. Insomniac's break is slightly longer. And I think Epic does, maybe not Epic. No, I think Epic does something like this. In general, companies that do breaks like this, it's like really, really, really healthy because you can unwind. You're like forced to unwind. You know nothing. If you leave on vacation, there's this temptation of, should I check work email? Maybe it's really important. Are they all right there? All of this is like, no, don't work, just relax. So basically next weekend I'm gonna leave, I'm flying to Canada and I'm gonna spend a week there. And then there's New Year's, and this was the last chance for me to do the stream. So with that, thank you all very much for sharing this with me, sharing the space with me. And if there's future things like this, you know, my Twitter, so subscribe and all of that. Thank you all.